Hello friends, this video on DNF block elements part 15 is brought to you by examfear.com. No more fear from exam. If you talk about the atomic size, you talk about the Lanthanide contraction also. In fact, we'll talk about this once again. It's a pretty interesting topic. What is Lanthanide contraction? See, greater than expected decrease in the ionic radius of the elements in the lanthanide series. From the atomic number 57, this is my 57, to 71. So actually this whole thing, lanthanide series. So if you see from cerium to lutetium, there is a decrease, a huge decrease in the atomic size. 204 again decrease, 203, 201, 199, little bit stable, again 186, 194, 192, 192, 189, 190, right? There's a decrease. This is unexpected decrease, greater than expected decrease in the ionic radius. And with this, the impact is that the next elements are all the more smaller. So if we talk about the lanthanum, for example, the atomic size is 1207, but the next element is, if you see, 175. There is a huge difference now, right? See, if you see from 57 atomic number, 58 comes here, it's somewhere outside. But actually when you compare the whole P6, you'll talk about lanthanum and hafnium, you'll see that there is a huge decrease in the atomic size. And the trend continues actually. From here, the size keeps on decreasing. That is the result of this contraction. Okay, so from 72 onwards, atomic number 72 onwards, if you see, there is again decrease, but since there is a extra decrease here, so if you compare, this is a huge decrease, right? Because of this, there is a trend here. If you see here, one thing, if you go down the group, we have seen that the number of shells increase and the atomic size increase. So if you see 170, 190, 207, this is perfectly fine, right? But if you talk about this particular series now, 160, 175 is fine, but if you see it's 175, it's all same. 153, 164 increase, but 164 to 170 almost same. 139, 154 increase, but there's a very small increase here. 139, 147 huge increase, again there's a very small increase. 132, 146 huge increase, almost, in fact this has decreased now. Similarly 126, 142 increase, then again there is a decrease. 124, 139 huge increase, again there is a decrease. 132, 145 there is a huge increase, again there is a decrease, right? So here also this is increase, 122, 144, but there it decreased. So our normal trend that as you go down the group the atomic size increase, that is not true. It is true only for this one. Why? Because here the lanthanide contraction impact is not there. Only from hafnium the impact is visible, because these elements actually decrease the size. Okay, this is called lanthanoids contraction, and this is because of poor shielding effect of 4f electrons. So if you notice that we have told that for lanthanum the electronic configuration was xenon 4f0 5d1 6s2, right? Lanthanum, this is lanthanum. After lanthanum the next element is HF, hafnium. So if you see the electronic configuration for this is, in this case we have told you that since D already has one electron now, the energy of D orbital has increased 5d. Now the next electron will go to 4f1, right? And the trend continues actually. Again the next electron will go to 4f2. This is 4f1, this is 4f2. The trend continues. Okay. So this is my, this is my lanthanum. Then you have cerium, this is for cerium. I'm talking about cerium. Cerium is atomic number 58. Cerium, yeah. For cerium, this is the electronic configuration. And the next element, if you see, PR, Parsi dynium. For PR, if you see, the electronic configuration will be XE 4f2 5d1 6s2. Okay. Then again, the next element is ND, neodymium. For this neodymium, again the electronic configuration will be xenon 4f3 5d1 6s2. So if you see here, what is happening is the f orbitals are getting filled. F orbitals are getting filled in this. right? So if we compare the electronic configuration of, let's suppose, lanthanum to lutetium, the last element, the electronic configuration will be XE. All this 4f orbitals will be filled, then 5d1, 6s2. And after this, if you talk about hafnium, so in that case, actually this guy, then again my 5d orbitals will start getting filled. Okay, and that's why it is a d block element, hafnium, and these are all f block elements. So nevertheless, what I'm trying to say is, in all these, f orbital is getting filled, and f orbital has all the more poor shielding effect, correct? And because of this, if you see, if you go from left to right, you are increasing the number of electrons and number of protons. You're increasing the number of protons, that means you're increasing the nuclear charge. Also, if you're going from left to right, you're adding electrons to f orbital, and we have told that f orbital has all the more poor shielding effect, right? So that means if you're going from left to right, in this case, in this lanthanide series, you're adding positive charge to the neutrons, to the nucleus, but you're not shielding it properly, because the electrons are going to the f orbital, and f orbital has poor shielding effect. Thus, the whole, the elements contract, the atoms contract from left to right. Now, since we were at lanthanum, the size was 207, and then since all these orbitals got filled, and we came here back in this d orbital at 722 atomic number hafnium, we found that the atom size has already decreased a lot, and this decrease is called lanthanide contraction. And the impact we have seen, that the normal trend, if you go from top to bottom, the atomic size actually increase because you are adding extra shells, but because of this trend is not followed for transition metals. Okay, why this trend is not followed? Because of the lanthanide contraction. Why lanthanide contraction? Because in this lanthanides, my 4f orbitals is getting filled, and f orbitals has very, very poor shielding effect. Since it has very poor shielding effect, the contraction is all the more evident. Okay, so hope you understand what is lanthanide contraction and why it happens. It happens only because of 4f orbital. It has very, very poor shielding effect, and these elements actually, because of this, by the time you reach at this position, your atomic size is already decreased a lot. And if you can see here, there's a huge decrease from 207 to 175. Okay, and again the trend continues, because here also when you're adding, you're adding to now d orbital, and d orbital also has the poor shielding effect. So this also goes on, this also decrease actually. Okay, let's take one numerical on the atomic size. Why do transition metals exhibit higher enthalpy of atomization? So we have seen that what is enthalpy of atomization? It is nothing but the energy required to convert 1 mole of substance in stable state, 1 mole of stable state substance to its gaseous state. Right? When you talk about metals, transition metals, it is normally solid. For example, iron solid to iron gas. Okay. Now, to break solid to gas, you need to actually break all these metallic bonds. These in the solid transition metals, they are solid, they are hard. Why? Because they are held together by strong metallic bonds. And we have seen that d and s orbital, both these orbitals, electrons are involved in metallic bond formation. Correct? Now, since both these are in, and we have 10 from D almost and 2 from S, 12, maximum 12, but that's not the case. Maximum you can have 5 here and 1 here, 6 electrons, again a huge number that's involved in the metallic bond. Why 6 I took? Because unpaired electrons are typically involved in the metallic bonds. Yeah. So that's why, since the metallic bond is strong, because of the number of unpaired electrons, they have high interatomic interaction, and thus they have high enthalpy of atomization. Okay. The next question is, in the series scandium to zinc, the enthalpy of atomization, zinc is lowest. Why? I told you this enthalpy of delta H and let me write it clearly. So this value actually depends on what? Number of unpaired electrons, because these unpaired electrons forms bond, the metallic bond. So if you talk about the zinc, the electronic configuration is Ar 3d10 4s2. It doesn't have any lone pair of electrons. If you talk about the d orbital, 1 2 3 4 5, 1 2 3 4 5 6 7 8 9 10. There is no unpaired electron. In fact, you talk about S also 4s2. There is no unpaired electron, right? So if there is no unpaired electron, the bonding will be weak, and thus it has lowest enthalpy of atomization. Thank you. Visit examfear.com to watch more videos, attempt free online tests, get free study materials, find tutors and mentors, and much more. Thanks once again.